In this video we're going to look at inverse functions, how we start with an original function and we convert and we find its inverse function. Okay, consider a function f which maps each element x of the domain x, big X, onto its image, small y, in the range, big Y. So that means you've got f is such that it takes x in the original place, original element, to the new element. So this is where x belongs to the set of reals and y belongs to the set of reals. Okay, that's a wee bit confusing. Let's look at this in a wee diagram. So you've got, first of all, you've got your domain x. So your domain is where you start. Big Y is where you finish. And it's your codomain. And we're going to be focusing in on the range. So you've got x, and we're told that x goes to y. You maybe had another element a. It maybe goes to b. Maybe you have another element c. And maybe it goes to d. So x goes to y. So you say y is the image of x, a goes to b, b is the image of a, and c goes to d, so d is the image of c. And x is the domain, so where you start is the domain. So x is the domain, is where you start, and y is the range, so y is where you go to. So these things are where you go to. There could have been another element. There could have been another element e, maybe not in your codomain, this is called your codomain, but this would not be in the range, so it's an extra one here. So if I looked at this, just the things highlighted are in the range. That's where the things you actually go to. E is maybe in the set of reals, but it is not actually what one of my things go to. So not everything in the set of reals has to be covered. Okay, so the inverse of f is the function f to the minus 1, such that f to the minus 1 takes y back to x. So basically, we could redraw this thing here, and you would start with your y, which was y, b, and d in our case, and it would take you back to x, which we had said it was x, a, and c. So y goes back to x, b goes back to a, and d goes back to c. This notation, by the way, of inverses you have seen before, because remember, sine x, you maybe had sine x, and the inverse of sine was sine to the minus 1 of x. Okay, so, and that's on your calculator button. An easy way to remember, they're on the same button on the calculator. If you do shift and sine, you'll get sine to the minus 1. Likewise, shift and cos, you'll get cos to the minus 1. So this is a notation that you are already familiar with. Couple of key points here. A function has an inverse only if it is a one-to-one. So here, this function f, which took my elements x to my elements y, it was a one-to-one function. You can see one element goes to one and only one element in this in the range. And if you reverse it, it is still a one-to-one. So that's why it has to be a one-to-one. If it's a one-to-one, it's a one-to-one originally, then the inverse is also going to be a one-to-one. And the range of a function will be the domain of the inverse. So what that means is, the range of my original f function, here was my, I'll label this one, this was my f function. The range of my f function was y, b, and d. And the domain of my f to the minus 1 was y, b, and d. Likewise, the domain of the original function was x, a, and c. And now the range of the inverse is x, a, and c. And very key point here as well, and we'll see this when we look at our inverse trig in a later video. It says the inverse of a function is a reflection of the original function in the line y equals x. Okay, this is a wee trick really for how we can do these. So it says the basic method is to let the function equal y and then switch the x and y variables. We then rearrange the function to make y the new subject. So I'm going to do this with this function. This is y is equal to 2x plus 3, and I'm going to put in a couple of numerical examples just to show you that it does actually work. That's a great method. Okay, let's look at this example. But what I actually do it slightly differently. What I'm going to do is I'm going to rearrange to make x a subject, and then I'm going to switch the variables. That's always the way I do it, but it doesn't really matter. You could do it the same order as I have up here, or do it the way I'm about to do it, so it doesn't really matter. So I'm going to just make x the subject. So make x a subject. So to do that, I'm going to just say y minus 3, first of all, is equal to 2x, which means x is equal to y minus 3 all over 2. And then all I would do is just rewrite that as y is equal to x minus 3 over 2. So what I've said here is I've said the inverse of y is equal to 2x plus 3 is y is equal to x minus 3 over 2. So we're going to test that out, putting in a couple of numerical examples into the original equation, and then we're going to use our new inverse function to see if it takes them back to where they started. Okay, so I'll do this in a different color. If I had put x equal to 1 into my original equation, so when x equals 1, y would be 2 times 1 plus 3, so y would be equal to 5. Now if I put x equal to 5 into this equation here, what would I get? So hopefully it takes me back to 1. That's the hope here. So we have 5 minus 3 divided by 2 is the same as 2 over 2, which is equal to 1. Okay, so let's look at what we've done. I put x into this function here, and it gave me 5. So that means my x goes to 5. And then I made x equal to 5 my starting point. So I made 5 my starting point, and I put 5 into this function, and it took me back to 1. So I've done my first function, and 1 goes to 5. And then when I put in the inverse, 5 goes back to 1. So I know it works. It is absolutely fine. I wouldn't do this in an exam. This is just really to explain to you that this does work. Okay, we're going to just put in a couple of different examples. I'm going to put in, just to show you that we can do this the other way around, that if we had started with this function, if we'd started with this function, then we can go back and put it in. So I'm just going to pick any random number at all. I'm going to pick 10. So if I put x equal to 10 into this function down here, then y would be equal to 10 minus 3 over 2. So it's not a very nice number I've got here. It's going to be 7 over 2. And then if I put 7 over 2 into this function over here, it should take me back, if I've done it correctly, it should take me back to 10. So let's see. So when x equals 7 over 2, y is equal to 2 times 7 over 2 plus 3. And then that's a nice easy one. 2 times 7 over 2 is just going to be 7 plus 3 is equal to 10. So you can see it doesn't matter which order you do them. As long as you do them consecutively, you will end up in the same place. Okay, same idea in this question. I'm going to just say let y equal 5 over x minus 5, just because it's easier than writing down g of x every time. So what we want to do here is make x a subject. So I'll just say make x the subject. So apologize for my bad handwriting. So I'll bring that 5 across. Y plus 5 equals 5 over x. That means x upon y plus 5 is equal to 5, which means over here x is equal to 5 over y plus 5. And then just rewrite as g to the minus 1 of x. So that's how we notate the inverse function. So the inverse of g of x is equal to 5 over, and remember, change your y back to x, so 5 over x plus 5, and that's it. Same idea in this example, just say let y equal 10 minus x, and then we'll rearrange. I'll just say rearrange this time. Rearrange to make x a subject, so x equals 10 minus y, and then we'll just rewrite to give you y is equal to 10 minus x. So that means h to the minus 1, the inverse of h is equal to 10 minus x. Okay, this is bizarre. Here we've got a function, it's equal to 10 minus x, and its inverse is 10 minus x. So it is self-inverse, you could say. Right, we're going to look at a couple of numerical examples for this one just to see if it works, because it is a strange thing, and then we're going to see maybe geometrically is there any transformations which maybe are self-inverse, so any times this would happen as well. Okay, we're going to put x equals 5 into this to see what happens. When x equals 5, h of 5 would be equal to 10 minus 5, which would give you 5. And then we're going to put x equal to 5 into our h to the minus 1. So h to the minus 1 of 5 is going to be equal to 10 minus 5, which equals 5. So we've shown 5 goes to 5. Now we put 5 back into the inverse, it takes you back to 5. Okay, we're going to pick a different example and see if this still works. So let's see, we will pick, I'll pick anything at all, we'll pick 9. So 9, h of 9, putting 9 into your h gives you 10 minus 9, which gives you 1. So we're starting with 1. So I put 1 back into your inverse function. H to the minus 1 of 1 is 10 minus 1, which gives you 9. So we've gone from 9 has taken us to 1, and then our inverse has taken that 1 back to 9. So you can see it does work. Okay, it says the function f is defined by f is such that it takes x to 1 minus x over 2x plus 1. And this is where x belongs to the set of reals, where x is greater than or equal to 1. It says state the range of the function. So the range of the function means where does this actually go to. So we start in your real numbers such that x is greater than 0, but where do we end up to? So effectively, what are your y values, or in this case, your f values? Right, I'm not going to know just by looking at this equation here, looking at the function here, what my range is going to be. So a good idea would be to sketch this equation. So first thing I'm going to do is I'm going to divide. And the reason I'm dividing is because I've got a fraction, and the order of the fraction is the same as the order of the numerator, is the same as the order of the denominator. So a good practice is just to divide here, and you'll see why in a wee second. So by the order I mean the power of the x's. Power of the x on the top line is 1, power of the x on the bottom line is 1. So if you're ever in a situation where your order of your numerator is greater than or equal to even to just the order of the denominator, a good place to start is to divide. So I've just set out my division sum, and I'm going to just divide. So I'm dividing my x minus 1, my numerator, by my denominator, which was 2x plus 6. Now to do this, I'm going to think, how many times does 2x fit into x? Or what a better way of saying it is what I need to multiply by 2x by so that it becomes x. So 2x would need to be multiplied by 0.5 to become x. And then you do your 0.5 times your whole of your divider. So 0.5 times 2x just gives you x. 0.5 times the 6 gives you 3. And you write this down underneath. Now some people put a wee minus here. I wouldn't put a minus here, but I would just know what I am going to do now is subtract x plus 3, take x plus 3 away from x plus 1. So looking just at this line here, looking just at these two, I have got plus 1, sorry I haven't got plus 1, I've got minus 1, and I'm taking away plus 3. Minus 1 take away 3 is minus 4. And then looking at this line here, I've got x minus x is 0, so they disappear. So that's what I'm left with. So I've shown that 2x plus 1, 2x plus 6 goes into x minus 1, it goes in half a time, and then my remainder is minus 4. So what we have shown, therefore we have shown x minus 1 being divided by 2x plus 6, it goes in 0.5 whole times. And then you've got a remainder of minus 4, so you write that as minus 4 over 2x plus 6. And then this second bit, then you can cancel that down a wee bit. That's going to be 0.5. I can't change that, obviously. But my fraction, top line divides by 2 to give you 2. Bottom line divides by 2 to give you x plus 3. So what I have shown is my f of x is equal to 0.5 minus 2 over x plus 3. Okay, we're going to do a sketch now of this. We need to just remember what our graph, we've got a reciprocal graph in here of some description. Let's remember what 1 over x looks like. So we'll be rubbing this out in a wee second, but 1 over x looks like this. Top right, bottom left. But our thing here has got a minus 2. So it's minus 2 effectively is on our top line. So y is equal to minus 1 over x is then the opposite two quadrants. So it's top left and it's bottom right. So we know the general shape of our graph will be this. Now the plus 3 in the bottom line on the denominator and the 0.5 are going to change the location of the center of it. So instead of being the origin, our graph will have like a different center point, if you can imagine what I mean, as you'll see in a wee second. So we're going to look at how we can draw this. Okay, I've just shrunk down my y is equal to minus 1 over x over here, this graph. So remember, it's our graph is going to take this form, and that's because we've really got a minus 2 over x plus 3. So like this one over here, it is a negative reciprocal graph. So what does this, why does this graph have this, what's called a discontinuity when x equals 0? The reason this graph over here, and I'm talking about the small one here, why it has a discontinuity at x equals 0 is because 0 would cause there to be a 0 on the bottom line, because you'll have a 1 divided by 0. Anytime you have a 1 divided by 0 or something divided by 0 in mathematics, it's going to cause some sort of a problem. So over here, if you think what value would cause there to be a 0 on the bottom line, you've x plus 3 on the bottom line. So if you put x equal to minus 3, that would be minus 3 plus 3, that would give you 0. So x equals minus 3 is going to be a problematic value for us here. So here, x equals minus 3 is, excuse my handwriting, is an asymptote. Okay, just like over here, x equals 0 was an asymptote. So over here, x equals minus 3 is a vertical asymptote. Okay, so we've got that sorted out. So first of all, there's your graph. And there's x equals minus 3 is going to be an asymptote. We also need to figure out what this 0.5 does. So if you imagine you had this graph, y is equal to minus 1 over x, and then you added on a half, what would that do to it? So what it would do is we would just shift the whole graph up by a half. And so if it shifts the whole graph up by a half, that means the horizontal asymptote of the x-axis is no longer going to be an asymptote. The new horizontal asymptote is going to be at y is equal to a half. So y equals 0.5 would be your new asymptote. You can then draw your graph, and your graph as a sketch looks like this. So you can see similar to the one we have up here. Okay, right folks. Now don't draw that just yet. The reason why is we need to find out where it crosses this horizontal axis. So I've just sketched this. I'd imagine this is wrong. This could be on the other side of the y-axis. We do not know. So this is just a very rough drawing. So don't draw it just yet. Let's figure out what this point should be. So to find out where that is, we're just going to find out where it crosses. In fact, actually what we can do is look back at this and put in x equals 1 into this thing and see what happens when x equals 1, because this is defined from x equals 1 just, so x equals 1 and above. So that would be a sensible place for us to put in, a sensible value for us to put in. So we'll just say when x equals 1, your f of 1 would be equal to 0.5 minus 2 over, and that's going to be just 1 plus 3, which is going to be 0.5 minus 2 over 4, which is 0.5 minus a half, which is 0. So f of 1 is actually 0. So we have found, in doing it this way, we have found our what our graph looks like. That's a very messy looking graph. You can use your imagination. That's very roughly what it looks like. Okay, we're now ready to answer the question. So after all that, we're ready to do the range. So remember, our graph just exists from x is greater than or equal to 1. So our graph exists from this point outwards. So it exists out this way. And from that point outwards, the graph only goes from 0 up to but not including y is equal to, up to but not including y is equal to 0.5. So I'll just get that back there. Okay, so just to run through it again, very quickly, you've got our graph existed from here outwards, from the 1 outwards, and so on the vertical end, it exists from 0 up to 0.5. So we say our range, how you write it in, just say your range is, and then curly brackets, f belongs to the set of rails, such that, and then it's just 0 is less than or equal to f, because you're allowed to be 0, is less than 0.5, and then close your curly brackets, and that's it. Okay, so an awful lot going on there, but we've managed to get to our answer for our range. Okay, what we're now going to do, we've been asked to find the inverse of the function and also stating its domain and range. Now, stating the domain and range will be very easy, we'll see that at the end, but finding the inverse of this one is quite tricky. So first thing I'm going to do is say let y equal 0.5 minus 2 over x plus 3. Then all I'm going to do is bring the minus 2 over x plus 3 across and bring the y across. I'll have 0.5 minus y. And then I'll do a wee bit of rearranging. I'm going to show all my steps. Now you can skip these out, a number of them. I'm going to multiply across. So I'll have 0.5 minus y upon x plus 3. And then I'm trying to get x on its own. So what I've now got my x on the top line at least, which is good. I'll bring my 0.5 minus y back across, so that's equal to x plus 3. And probably what I would do here at this stage is tidy up the left hand side a bit. Top and bottom can be multiplied by 2 to give you 4 over 1 minus 2y, which is a wee bit prettier than having that 0.5. And so that's still equal to x plus 3. And then your last part of the rearranging then, make x a subject, x equals 4 over 1 minus 2y minus 3. Okay, and then you, of course, write it in inverse form. Inverse of f then is equal to, and change the y to x, so 4 over 1 minus 2x minus 3. Okay, the first thing from your notes, earlier on it says the domain of the inverse is the range of the original. So here, and vice versa as well, so that also the range of the inverse is the domain of the original. So the domain is going to be x belonging to, it's going to be x belonging to the set of rails such that 0 is less than x is less than 0.5, because remember that was our range of my original, and then the range, so this was my domain. So the range is the inverse of f belongs to the set of rails such that f to the minus 1, the inverse of f, is greater than or equal to 1. So if you remember back to the domain of my example earlier on, my original f, it was x greater than or equal to 1. So that's why our range of our inverse is f to the minus 1 is greater than or equal to 1. And that's that example done. Okay, this example says, given that f of x is equal to x minus 2 all squared, where x belongs to the set of rails, state the domain for which f of x can have an inverse, and find this inverse and state its range. Okay, right. Now, what it says earlier on in your notes here, it says, in the video earlier on in the video, it says that only a one-to-one function can have an inverse. So what we're going to do is sketch our original graph. So sketch this graph here, see what it looks like, and then see how can we restrict it so that it is now a one-to-one. So if we just sketch, so it's a U-shaped graph because it's a positive quadratic, and when x equals see where it touches the x-axis, put 0 equal to x minus 2. So that means x is equal to 2. So that's why it crosses at 2 here. So that's a sketch of the graph. I'll just put my y-axis. I don't know where the y-axis is going to be. But there we go. That's fine. And we have to look at where we can restrict this thing. So what we can't have is two x values going to the same y value. So at the minute, this is a many to one because there's multiple x values going to the same y value. So we have to restrict it and see what that happens. So if I was to cut this graph here, then that wouldn't happen. Okay, I wouldn't have the same two x values. So if I started my graph from here on, one x value goes to one y value, one x value goes to one y value, and that's going to be the same all the way along. So by restricting the domain, we can do that. So we're just going to say this graph becomes 1 to 1 if the domain is restricted. So the domain is x, still belonging to a set of reals obviously, such that x is greater than or equal to 2. So we have to think how we restrict it so that it becomes a 1 to 1. So that's what we've done. Next thing it says, after we've restricted the domain, it says find the inverse and state its range. So we have to actually find the inverse. So I will write down our equation, our function again. It was f of x is equal to x minus 2 all squared. So we'll just say let y equal x minus 2. And then I'm going to make x a subject. The opposite, so two things are happening to my x at the minute. You're taking away 2 and then you're squaring. The first thing to reverse is the square root, so squaring. So square root of y is equal to x minus 2. And then the square root of y plus 2 is equal to x. So we'll say then x then is equal to x is equal to the square root of y plus 2, which means the inverse of x is equal to the square root plus 2, and change that y to be x. That's what we've got. Okay, and we'll just say remember the range of the inverse is the same as the domain of the original. So the range of the inverse is the same as the domain of the original. So that means the range for our f to the minus 1 is going to be f to the minus 1 belongs to the set of reals such that f to the minus 1 is greater than or equal to 2. And you can see up here, it's even written down there, was our domain of the original was x greater than or equal to 2. So the range is f to the minus 1 is greater than or equal to 2. And that is us done for this video.